Yes, that is good then. Right, so you probably know the drill by now. So exam speech, exam speech, exam speech. Hour 15. List all the equipment. List all the instructions. List the information. Here's your paper. Check you got the right one. You may begin. So, as you know, they always give the funny exam speech at the start, which less time we spend doing that, the better. Okay, so we've got I've got the question paper and I've got the insert as well for what it asks. Okay, so first question. Internet. What are you? Right one. Can you still hear me? That's good. So question 1. We've got a graph over here showing some of the energy resources used to meet demand for electrical power in the UK on one day in 2020. Okay, so here's as the time of day progresses on from monitoring from midnight to midday. Okay, so our demand is our top line here. We've got gas as this dashed line, nuclear, and then we've got wind.
Could you refresh your screen, please?
Here,
I
which
can't see it.
goes down. And then we've got coal power. Okay. So
can you go up a bit? Okay, yeah. All right, can I see the question?
yeah. So the maximum demand for electrical power on that day was 6 p.m. To determine the percentage of maximum demand for electrical power that was generated using gas. Okay. I'll flip that back up to our diagram.
Is
What
it
would be your first
30,000?
step? So,
Wait, for gas?
Demand is where's my pen? There's my pen. So demand is 30,000. So D equals 30,000. Okay. So yes, you identified one. What is gases at the same time as that approximately?
Is it like
Again, you've got ability to draw, and so have I. So if I put as a line just about like that, that should hopefully help to clear it up a little bit.
I can't see what it's going up by. Hold on.
If you look on your gigawatts, you should be able to notice. So each big gap, each goes up by 5.
Okay.
That'll be 12.5, 15, 17.5, 20.
Okay. So it would go up in 2.5 every time.
2.5 is that midpoint. So every 5 is 2.5.
Okay.
So 25 per 5. You can think of everyone as being about 500. So 5, 1,000, 1,500, 2,000, 2,500.
It would be like 6,000. No. 6,750.
If I take away our line here, you can see where it is now properly. Look. Okay, so 15, 15.5, 16, 16.5, 17, 17.5, 18, 18.5, 19, 19.5, 20.
Okay.
So where does it fall on that line?
16,500.
Okay, so that is gas, there's my tool. So gas is equal to 16 500. Okay, so we've now got our two values. Okay, and you at least remember the mnemonic of RTFQ, because we did not want you to, at least you didn't pick the wrong to or anything.
Mm-hmm.
Okay, so on our next step. So now we've got the demand
Oh,
and we've
is
got the
it
power. We want to find the percentage.
16,500 over 30,000? And then
There
you
you go.
times that by 100.
Yep.
I
So
don't have a calculator on me, so.
I've got mine, don't you worry.
Oh, actually, never
See,
mind, I found it.
I think I have learned to keep a calculator relatively nearby. 16, 5, 30.
I got 55%.
Yep, me too. So 55% on that one. Okay, so where's my mark scheme? There's my mark scheme. 55%. There you go. And that there, reading from the graph, you see that there, we've basically just gotten full set of our full 3 marks. So getting your readings from the graph, mark 1. Mark 2 was, as you said, doing your division.
Mm-hmm.
Okay, and mark 3 was your correct answer. Basically. So I did pull it up somewhere in all of my useless tabs. So I think this one. This is the specification just over topics in general. So for trilogy, this might come in handy for you. So I'll just send you this link over so you can at least see what you're looking at. Okay, and help you to figure out if you need any help with any topics.
Mm-hmm.
Okay, I've sent you the link over chat just in case you wanted it. Okay. The UK government wants to reduce carbon emissions as much as possible. So
Coal and
which
gas.
energy? Yeah, coal and gas. Because just for extra
They.
credit.
Oh, I need to. Wait, do I need to explain it? I don't, right?
You don't need to, but just for a bit of extra credit.
Is it because when you burn coal, you release carbon dioxide?
Yep, and what
That's
are they
what-
called? Coal and gas, along with a couple of others.
Oh, fossil fuels.
There you go. Fossil fuels. So basically, all you've got to remember, if they ask typically about carbon emissions, you've got to remember about the fossil fuels. Okay, because nuclear produces nuclear waste and so on, but doesn't produce carbon emission. Wind, similar story. It doesn't produce emissions of carbon dioxide.
Mm-hmm.
Right. So a network of transformers and transmission cables transfers electrical power from power stations to consumers. What do we call this network? And you are on mute again.
Isn't it like national something? Like, is it like
Yes.
uh
National what? So
oh, National Grid?
there you
Is
go.
it?
For National Grid. Well done. That one there is just a simple memorization question. Okay. If you had it right, since it's going all over the nation, it's national, and then it forms like a grid-like structure. So national grid. Okay, so there you go. Last question. Explain how using step-up transformers makes the network efficient.
Um, isn't it when it increases the current back up? Right? Is it?
So
Step
first of
up?
all, do you remember your diagram of the national grid?
Yeah, there's like the
We've got the power
cable.
station
Mm-hmm.
here, we've got the house here. Okay, we've got the pylon going between them, like so, like this. And then as you know, we've got two transformers, one here connecting up to our power station, and one on the other side here connecting up to our house. So for starters, which one is our step up? The orange or the red transformer?
Step up is. Oh wait. Is it
Ignore it.
the yellow one?
It is, yeah, it is the orangey yellowy one.
Oh, okay. So it reduces the current?
Mhm. So first of all, it's always a good idea to identify where it's going from and to.
It's going from the it's going to the houses.
It is going from where to to the to the pylon slash to the grid.
Oh,
So because
I
remember
don't really
we
remember.
got the pylon in the middle.
Mhm. Wait, I can't see the screen.
Yeah, you had it. Got it right. So what happened?
Something.
So
I
and
think
you were
it's
onto it. So
sorry.
current. So as you said. So first of all, it's identifying what happens to the current and the potential difference. So of these two, which one goes up, which one goes down? Because remember, they a lot of the time with anything to do with national grid, they work in opposite. Which one up, which one down?
Um, the I think it's the current D. The voltage increases, current decreases.
Okay, so PD up, current down. Yeah,
Mhm.
that basically would if you other than the fact that I'm just drawing it out to make it a little bit more visual, basically just saying that current would increase potential difference, current would decrease, potential difference would increase, would net you 2 marks. Basically, so already just explaining current potential difference nets 2 marks. Third mark, so why do we do this? And you're on mute.
We do this so it reduces the energy loss, I think, because there's less heat created or
There you go.
something to do with heating.
There you go. Less energy loss from heating.
Okay.
Right. Okay. So as you said, so PD up, current down. 2 marks. And then last one is about the energy loss. There you go. You see, it's GCSE content is not as scary as it first looks, is it? Right, so that would basically be minus a slight bit of interfering. You got full marks on the first one. You see, even if you take a little bit of time to draw out sometimes or have a look a bit at the odd occasion. So especially with transformers, remembering which one's up and which one's down always comes in handy to just do a rough sketch similar to what I just drew of even just the crosses in different places of of the station one cross grid, homes, and then the step up and downs, just so you can see which one's where and which one you can imagine what each would function as. Okay?
Okay.
Right. So, new question typically means that we're changing topics. Okay, so question one, as you saw, was basically energy and national grid. Question two, we're now looking at heat capacity. Okay, and we're starting out with a nice and long question for today. So describe how the student could use the equipment shown in figure 2 to determine the specific heat capacity of vegetable oil. Okay, so imagine we've also got olive oil, which is obviously not in the diagram.
Can I just see the mark scheme for this one? Because I haven't done this practical in a long time.
Yeah. So there's my mark scheme. So you got 8 out of 8 for the first one. So before I show you the mark scheme, is there anything you can guess about it? About what you do?
So you measure some vegetable oil, you put it in the beaker, you place the beaker on the electric heater. Wait, what's the formula for specific heat capacity?
Now you're thinking along the right lines. Well done. So heat capacity is probably might be, here we go. Here it is. Here we are. So heat capacity. So change in thermal energy. The change in heat is equal to mass times change in thermal energy is equal to mass times specific heat capacity times temperature change.
Okay, so you measure the temperature at the start of the oil. Then you need to also measure the amount of you need to measure. Wait, don't you have to
we're getting the energy, aren't we? Because for starters, energy, what do we measure typically?
joules?
Okay, and what have we got here?
Joule meter.
So that's
Oh,
telling us
yeah,
that
I
we're
mean,
getting the energy.
yeah, for the mass, don't you like have to put the beaker on and then set it to 0? I don't know what it's
There
called.
you go. Yeah. Basically use the balances, tear it to 0 to make sure you don't get a 0 error.
And then you need to pour the oil in, measure the mass,
Yeah. Do
and then
you remember what the definition of heat capacity is?
no.
It is the amount of energy required to heat 1 kilogram of a substance by 1 degree. Do you remember?
I thought that was specific heat, latent heat.
Latent heat is about changing states.
Oh, okay. All right.
Latent heat is the state change. Heat capacity is the rising of the temperature,
Okay.
which you can see it's an indicator of the change in temperature from the fact that we've got a thermometer and we're monitoring, and it doesn't say about states, it says about the temperature. Okay, so like you said, you just from the equipment, you can get at least a good indicator yourself. Okay, you can tell we're going to be measuring the amount of energy transferred. We're going to be measuring the temperature change, and we're measuring the mass. Okay, so here we go. So here's our lovely mark scheme. If I take away my impromptu bottle of oil to show it was there. Okay, so like you said, measure mass of oil using the top pan balance. So that in itself would basically help you get to a mark. Measure the start temperature of oil using the thermometer, sort of thing. Okay, you already figured out we were going to do the change in temperature and the equation. Okay, so you can think of that as basically about 3 or 4 marks
Okay.
of including obviously measuring the final temperature, because that basically
Oh
one,
yeah, I didn't finish saying
no,
it. So it's
but you
okay.
can see what I mean of even
Mhm.
without remembering the practical in itself, just looking at your equipment and looking at your equation, you pretty
Mhm.
much figured out the method to it in its itself.
Okay. Do
Okay,
you
do you
know
see
what
what I
the
mean? Of
what other practicals do I need to know for paper one?
uh,
Specific.
I believe you've. Where's my thingy? No, no, get out the way. Because I did have this thing open. So this is a pretty in-depth, quick look at it all. Okay, so this looks at energy systems. What you can see is it's telling you worksheets, mark schemes. So there's probably the kinetic. So there's definitely some to do with the energy here. Because if I recall correctly, the ruler one is a typical. Typically, you'll at least either have one mentioning a ruler or to do with using balancing weights as such in this one a little bit. So energy
Oh,
transfer, like you said,
TT4.
we've got the specific heat capacity. Okay, there you go. It does give me the RPs. So RP activity 14, investigating iron to determine the specific heat capacity of one or more materials. Okay. So it does tell. I did send you the link over for the whole thing, and if
Okay,
you
I'll
click
go
into that,
through
you
it.
can see these ones. So
Mm-hmm.
you can happily wander through this in your own time, but you can see we've got efficiency, national and global resources, electricity. So you're definitely going to need to know your symbols. Okay.
Mm-hmm.
Current resistance, RP15, circuit diagrams. Okay, we've got our RP16, circuit diagrams, construct appropriate circuits, investigating the IV characteristics. Okay, RP17, so densities of objects and liquid.
Oh, okay, yeah, I think I know now.
Yeah, you can see it. This page here, which you should be able to find from the link I gave you. You should be able to see them all. So RP18, force and extension of a spring in forces and elasticity. This basically just tells you all of the RPs that you need to know. It's like even if you're unaware of the practical as such, so like this one here, you basically worked out near enough how you do it yourself with the equipment and the equation. Okay? Just from the just from our um just from our thermal energy equation, so heat capacity equation, you basically worked out how to utilize the equipment. Okay, and I'm sure, and with what you gave there, that was basically a 3 to 4 mark. So we'll be generous and call it a 4 mark out of the 6 mark. So
Okay.
there, just from what you were saying.
Okay,
Okay,
that's okay. Yeah.
just from what you were saying, you basically worked out how to do this by yourself.
Wait, what
Okay,
were
so
the
give
points I missed? Wait, can I see the
the
max?
points you missed were mainly on about the energy
Okay.
transfer using from our joule meter. So
Oh,
basically,
okay,
you
yeah,
were
yeah.
the only bit you
Yeah, I
missed was
could do that.
about using the joule meter. So the energy transfer. That was all.
Okay.
Because that's the only part that then makes up that last bit of the equation, you see?
All right.
Okay, because you basically, where's my pen highlighter? Work here. You basically worked out the mass bit yourself from the scale, from the balance. You worked out the temperature change thanks to the thermometer. Only bit, of course, that you didn't really mention was our thermal energy. Okay?
Mm-hmm.
So basically,
Isn't
you
that
can
just
see
like,
how that,
how do you calculate that? Is it just like
if you look at, where's our
2 meter?
equipment? Can you see our joule meter just would have gone from 0 up to a certain figure. So
Oh,
that's
okay,
our
so it just
change.
change. Okay. All right.
Similar to like if you had a thermometer set to 0 degrees and then you heated it up to room of about 20. The change would be 20 degrees, even if it didn't seem like it. Okay, so give one risk when using the equipment above. Risk,
Um,
not
the hot
not error,
water.
risk.
You could ban yourself from the hot water.
There you go, burns. Because you're both using an electric heater, and if you look, as I say many times, RTFQ, it is oil, not water, which means that especially with oil, when it gets hot, it starts spitting and burning. Very nice for burns. Okay. So we've got a, and here comes the slight break in the scenario. So a different student did not have a joule meter and calculated the energy transferred by the electric heater. So physics equation sheet, energy transferred, power and time.
Isn't it E equals PT? Wait, no, it's not. Wait, power equals energy over time.
There you go. So P equals E over T. Okay? Yeah. So that's basically one mark in it. That's another mark in itself. Okay? Right, next part. So electric heater has a power output of 50 watts. Calculate the amount of time taken for the electrical element to transfer 4,750 joules to the vegetable oil. Okay, so first, what's our first step? And muted again.
Okay, so you would do power. Wait, no.
So
Energy
for starters,
divided by power.
what are our values? So P equals 50. Okay, so
50.
always identify the values.
Energy is 4,750.
4,750. Okay, so then you know we've got T is our unknown. Okay, so our normal equation is like this. Okay, so do you remember so in terms of if we had this as a pyramid, you can see it, this would be how our pyramid looks a bit more. So
Isn't
P,
it
E, and T. So if we want to find time, what would we do?
I got 95.
And I'm guessing that you basically did that equation. So
Yeah.
yep, that works. Let me. I've got in the old habit of turning my calculator off every time I'm done with it. Yep, I got as well. I need my controller back. Yep, so that's a mark there. And 95. There you go. So can you see what I mean by identify? Just substituting in your values is it's just a good way to start it. Okay, because that typically, even just substituting in what your known quantities nets you a mark. Okay, then the next one you get from the arrangement, and the last one you get from an answer. Okay, that's typically how our mark schemes go. That makes sense?
Yep.
Right, here we go. So in a deep fat fryer, vegetable oil is heated by an electrical heating element. Food is then cooked in the hot oil. A deep fryer contains an electrical component to monitor the temperature of the vegetable oil. So figure 3 shows how the resistance of this electrical component changes with temperature. So from the fact that it's mentioned temperature and an electrical component, that should give you a pretty good indicator as to what this component is. And yes, you're on mute again.
Is it a heater?
No, what is resistance, electrical component, temperature? You've been given the 3 main clues. Where's my...
Is it just a resistor?
Not quite. Resistance, you know. So you've at least identified now it's a resistor of some type. So an electrical component, them two terms together means it's going to be a resistor of some kind. The main giveaway term, though, is this here. What resistor goes based off of temperature?
Is there? Oh, it's something. Is it the temperature thing? The thermistor? Is it?
There we go. It's a thermistor. Knew you'd get there in the end.
I have a question. Are thermometers and thermistors the same thing?
Not quite. Thermistors are to do with the resistance in a circuit. So
But actually, would I get a mark if I put thermometer?
nope. And surprisingly, they haven't put that in there. But it wouldn't give you the mark because thermometers don't connect to the circuit. So there's my pen. So you know what? Let's use something actually slightly more useful than a pen tool for once. This is I spend too much time with with technology. So you won't need to know about it in terms of actually using it for anything of much use, but this site is good for at least doing diagramming. So complex sort of diagrams. And that even though you won't really need to know it. So there's my thing. Where's my bar? Get out the way for now. I need more shapes. I know it'll be in no. Mm. There we go. I had a feeling it would probably be in one of these things. Actually, no, I swear we got I know, I thought we had the basic ones in here. Did they get moved because of... Eh. Oh, well. I'll use them because you can see how these things get used a little bit more often than most of the time. So anyway, so that's what I was looking for. Get this out of the way. Get you out of the way. Get you out of the way. Yeah, so get you out the way, get you out the way. Over here, you. There we go. So anyway, electrical. So if thermometer doesn't go into a circuit, so where's my diodes? No, I am after LED. Where would they put them? Yeah, this is I barely ever look into this sort of area, but because you can see it, they do at least label their components, so which is useful for me. So we got our switch as usual, with some description anyway. We'll put the regular one in because you're probably more used to seeing that. No, no, yeah,
What's the
that'll do.
difference between that one and the other one that you put in?
Just the way the switch functions. So we'll use this one here just to represent our quick diode because this is probably the figure you're most familiar with as such, with one looking like that. Okay, and then we got our resistors. And where are you? You're the timer, you're the variable.
Isn't the one with the arrow?
It's that's a variable one.
Oh,
Might be in terms of what you've seen, but it's more of a case of it's just useful to. It's more of a case it's just easy to show you what. So anyway, we've got our ammeters and our voltmeters. Ignoring the very awkwardness of. So I know there used to be an easier section with all of this in, but I guess it's gone off or gone walkabout a bit. Oh well. Because I normally don't use it for this for very much here, but there's our cell. Where's our thermistor goes as what? Thermistor goes like that. Got it. Thank you. So it's basically the sort of box version of that wherever they have put it. Not in the vacuum, not in the waves. Yeah. We'll just use that one because it's close enough. So you're at least familiar with these symbols at least look slightly familiar, yeah?
yeah, I'm familiar with them.
So like you said, so thermometer doesn't go in a circuit diagram. We don't see a thermometer in a circuit diagram, but we do see thermistors in a circuit diagram. Okay, so for the sake of things, okay, we shall have our current going this way round as such. Okay, so we've got switches there. Our diode fits in this way. Okay, then it goes along to our thermistor, which we will connect up. So can you remember which goes in sequence, which goes in parallel? You remember voltmeter goes in what and ammeter goes in what?
Is this for the specific key capacity practical?
This is just for, because you need to know your circuit diagrams and this sort of area in general, but yes. This also applies to our specific heat slightly. Yes, you are on mute again.
Wait, did you ask me a question? I didn't hear you.
Yeah, can you remember which way round? So which goes in parallel, which goes in series, the voltmeter and ammeter?
The ammeter goes in series and voltmeter goes in parallel.
Yep. Ammeter in series, voltmeter in parallel. Ammeter goes round and voltmeter we will put over our, we'll just put over our resistor. Okay, so you at least, so you've remembered that at least, which you, okay, so that is basically a circuit diagram. So other than the fact that this diode in our question, the diode is that heating element though. Okay,
Yeah, okay.
so that's what it is that diode is basically our heat element. So the thermistor is our temperature checker. Okay, so that controls the resistance. Okay, so the electric heating element in the deep fryer automatically switches off when the oil reaches a certain temperature. Okay, so so we've got determine the resistance of the electrical component when the heating element is automatically switched off. Okay, so for starters, where in this diagram is our element switched off? You can see.
No, it's wait 3.4?
So that's
3.3?
3 seconds there.
Is it
So
like
that would be
3
about
point
3.2. Okay, so that's 3.2 and 150. So 3.2 and 150. Okay, because
wait,
that,
isn't it like more like 3.3? Because like it's in the middle of like 3.2 and 3.4.
okay. So 3.3 and that would be 155, 65, 75, 85, 95. So they're about increments of 5, so that would be about 160. Okay. So next up, what we now know is we know where it's turned off and the temperature it is turned off at. So now we need to determine the resistance using this diagram. So first of all, which value are we using? Our time or our temperature value?
Isn't it temperature? I found
Mm-hmm.
the value and I tried to go up. I think it's around 2,400.
So there's our value is here. Where's my blobby tool? There's my blobby tool. So our value, so 55, 60 is here or so. Okay, so that is 200. That makes 300. Okay, so 100 is split up by 5. Okay, so I think that makes an increment of 20 every turn. Yep, that makes an increment of 20 every turn. So 220, 240, 260, 280, 300, 320, 40, 60, 80, 400. So it's about 20 every increment. So 220, 240. Also to
Okay,
240,
yeah.
250, we could say, yeah?
All right.
Do you see how that works? Do you understand how we got to that value?
Yep.
Okay, so we can call that value of about 200 and what did we say? 50. So where was it? So it's this one here, 20, 40, yeah, about 250. Okay, so where's our mark scheme? There's our mark scheme. There you go. Bang on. Okay, so you would have got 1 mark from just getting the temperature and the other mark from getting the resistance. So, and also it does give you a slight range, so between the 40 and 60. Okay? So does that all make sense to you? Is making sense to you now? Okay. So some chips were put into our fat fryer. So in the fat fryer, the water in the chips underwent a physical change and became steam. Why is this a physical change?
Water will recover its original properties if the steam is cooled.
Yep. Right. And that's another mark. So basically, from question 2, which is worth 15 marks, so an indicator of maybe spending about 15 minutes or so on it, you basically earned 13. Okay? And the only ones you actually dropped were just a couple with the practical question at the start. The rest of them, even though it took a little while, which took a bit longer than would have been recommended, you got to in the end. You see? Right, question 3. Or at least start going through it anyway. So, question 3. Trampoline is made from a sheet of material held in place by stretched out springs. So figure 5 shows a child on said trampoline. Okay, so position A to position B. And just from this diagram, can you guess what we're looking into?
Gravitational potential energy and elastic potential energy.
Yeah. So, position A shows the child's maximum height above the trampoline, and position B shows the lowest position reached by the child when landing on the trampoline. So describe the changes of the source of energy in the child, springs, and surroundings as the child moves from position A to B. Okay, so if you look, this is worth 4 marks basically. So you can imagine they all link up together. But you can imagine at
Wait,
least.
can you quickly tell me the 8 energy stars and the 4 pathways? I think I need a quick fresh up because I haven't done that for ages.
Okay, so let's move it down. Okay, so you've got, as you'd imagine, you've got gravitational. Because even just looking at the hint in your
Oh no, I know how to
scheme.
do the question. I just want to have a fresh up on the 8 energy stars. Like what is it?
Okay, so you've got
Not heating. Thermal,
so you've got thermal,
gravitational.
gravitational,
Elastic,
kinetic, elastic,
and I don't know the rest.
chemical,
Magnetic,
magnetic, electrical, I believe.
nuclear.
Nuclear, I think we don't class in these.
Wait, what are the rest then?
These doors. Leave that. So there you go. Magnetic. Got it. So kinetic, chemical, elastic, potential, gravitational. Hey, there's nuclear. So nuclear counts, and thermal. So you
Okay.
basically got to them all. So starters. What would be our energy stores in these cases? What energy stores can we guess at?
So gravitational potential energy, then when she hits the trampoline, it changes into elastic potential energy. And then
But how does she hit the
no,
trampoline?
no, gravitational potential energy to kinetic and then kinetic to elastic.
And also, if it's a body of something, what is that body producing into the surroundings?
Wait, isn't it chemical as well? Because the child's energy will be used up.
hmm So thermal, chemical, so chemical slash thermal, like you said. Okay, so gravitational, kinetic, okay, elastic potential, and internal. So you got the energy stores, you just needed to explain what was going on with the increase and decrease. That was all, which you basically did. Okay, so gravitational decreases because they're going down and they're coming out of the limbo of having potential to go down. Kinetic energy increases because they're moving. So that's basically the child. So the springs, we get them stretched with elastic potential. So elastic potential increases. Okay. And the surroundings, we're getting that extra bit of thermal or chemical, as we put it, as well. So that's where our energy stores change. And so basically, your with the explanations included, would have netted the full marks because you got the energy stores at least. Okay.
Yep.
So when the child is in position A, each trampoline spring is stretched by 0.56 meters. Elastic potential energy is 4.9 joules. Child position in position B, it's increased to 8.1 joules. So we want the extension of the spring again. So we're elastic potential, here we go. So half spring constant extension squared. Okay, so 1/2 K, so constant, and extension. E squared equals equals our potential energy. Equals
Sorry,
E.
my audio is
Okay,
lagging a bit, so I'm gonna
it's
be
fine.
in the chat.
No, it's fine. I'll pop my chat window out then. There you go. Right, so we've got our equation. Yeah, so next, as you know, what's our next step? There you go. Well done. So substitute, as you said. So we've got EK. So EK at the start is 4.9. Okay, and we've got 4.9, and then we've got another value here. Elastic potential again of 8.1. We've also know one of our extensions. Okay, so we know one of our extensions is equal to 0.056. Okay, and we want to find our x value because, as you know, mathematicians like their value of x, like the value of x, and we've got our k value. Okay, so we've got a k value. So k this, k that. And then we want our little squared term because it is a squared value after all. In this case. And then it's all divided by 1/2. So times 0.5. Okay. Let me move my mess around a bit. Okay, so we want that there as well. And then we want our little squared term there as well. So that's basically our sort of equation. Obvious, other than that, it would just mainly be that would be in its own little set of brackets. Okay, just to keep the squared from affecting the whole term. So what's our next step? So just this would basically have netted you a mark minimum just on substitution, look. So substitution here, look, just nets you a mark. Okay, so that there, just the top line would have netted you a mark. And along with, again, so next step, what do we do? Okay, because for now we can ignore this bottom equation because we haven't got all of our values. Yes, so you said, so take that away. So take away our 0.5 and times this by 2. So 4.9 times by 2, we get a value of 9.8. Okay, so I will change my pen color to keep it going. So we get 9.8 as our second value is equal to k e squared. So nearly. Next step. So if we've got this as an equation here, next, don't we want to get rid of this squared term? Okay, so next up is sorting our square term. So square that value. Okay, so 0.056 squared is 0. The text tool. I'll put it in a red. So it is 0.0031336 K. Now that's basically what 9.8 is 0.03136 for K. Yeah. And in theory, fingers crossed anyway. Yeah. So from that, like it says, we get 3125. and I am not. So for that, now we know our K value. So where's my, we'll put this in our good old purple. So K is equal to 3, 1, 2, 5. Okay? That is now our value. So now what we have is a K value and our value here. So now in this equation here, we've only actually now got ourselves one on unknown, really. Now, if you look at it that way, we've only got one unknown now. So working out if we look at our mark scheme, working out our K value and then substituting here just gives us 3 marks. Can you see? So that gives us 3 marks because we want our extension. So I'll show you the rearrangement shortly. So as you worked out before, we divide by 0.5. So times 8.1, 8.1 times 2.
Next lesson, can we do more 6 markers? Because you know
Yeah.
ones that use more than one equation. I need to work on them a bit.
Perfectly fine. I mean, if anything, I'm more than happy to show you through maths. So 8.1 times 2 is you get 16.2. 4, so 16. So we get 16.2. 0.2 is equal to kx squared. Because remember, our equation is half ke squared, and we want to find our extension. Where's my highlighter? Let's put it in neon blue just to make sure you can still see what we're looking for. So we're looking for our extension there. Okay, so 16.2 divided by the 3.125. By 3. So divided by 3.125. And I hope this is a similar. Yeah, this looks to be about right anyway. So all that is doing is just doing it in one step while I'm purposely showing you through the step. Okay, so 16.2 we do over start 3.125, which giving us a lovely fraction, we end up, thanks to calculator math, we end up with 81 over 1, 5, 6, 2, and 5. Okay, so that's what we end up with. So x squared, so our extension squared. Okay, so our extension squared that we had at the start here, so, and the value that we're looking for, which is e squared, is that. So this is why we square root it, because we only want e, not e squared. Okay, so what we do is we square root this in order to get our e value. Okay, which square rooted, very kindly, it's a very nicely, it's a good number for them to give us for once. So you can probably guess the top number of our fraction, can't you? You guess the top number of our fractional e.
But I couldn't hear you properly.
Can you guess the top number of our fraction? So e fraction here. Can you see our square root fraction?
Isn't it 9?
Yep, so it is 9 over 1, 2, 5, because they do try and at least make it friendly. So that is your fraction, which brought out as a decimal, we get an extension of 0.072. And if we look, that is correct. Okay, and you can see, even if you got the K value wrong, you could get the rest of the marks from what is known as the carryover error. Okay, so can you see why we do the square root here?
Yeah, I get it.
And
Yeah.
everything now. Like I said, even if it, especially while I'm doing it, it has many more steps as you can see, but you can see how it works. So it's like if you were to do it, you could easily have done all this square root and fraction in one kind of thing, which would have been perfectly allowed.
Yeah.
Okay, but as I said, I split it up just to show you how it works a bit better. Okay, so I will clear up all my ink on this thing. So this here is the full workings. So here's our equation. Here's it rearranged. So basically, substitution and rearrangement, as well as calculation, gives 2 marks. Substitution part 2 gives another mark, basically. Rearrangement is another mark, and answer is a mark. So you can see why I say show your workings. Or show all workings, depending on what they kind of class it for. But that would have netted the full 5 mark. And if you were doing it in actual rush fashion, as such, so you'd have noticed straight off the bat you would have had your equation sheet with the half k squared. So you would have noticed, okay, I got the e, I got the first value. I don't have if we look, I've got the value here and I want the e. So we can tell from this, we're going to need to work out our k value. So we're going to need to work out our constant. Right, so next up, what we do is we look, okay, how do I rearrange my equation? Get my constant. So so it's going to be 2e. Okay? And then we square up, it's going to be 2 elastic potential. So we know double one value. Okay, if we've got the e on the first one, it means that we know to square it. So we pull that up with k. Okay, because remember in equations, sometimes that we work on both sides, but we eventually get to our answer. Okay, so you might have been told in maths, try and put all the numbers on one side and all of the letters on the other. Sometimes you might find it easier, especially neater, to sometimes keep it split apart, weirdly, like this. So after that, we now know, okay, we've got a certain amount of k and a certain amount of e and a certain number here. Okay, we need to divide this to give us only 1k. Right, there you go, value for k. So we've got e, we got k, we got half. Easy enough, do our maths with the k in the half. Okay, we've got e equaling that value, e squared, e equaling that value, e squared. Divide by this value here, then we just do a square root and we've got the e value. Okay, and especially if you've got a calculator, you can just put it all together in one place as such. Okay, is that all good and made sense to you for today? That's good to hear. Right, and I know I have gone over time again, as always. I don't think, have we ever actually had a lesson that's finished actually on time properly?
No, I don't think so.
Either way, right. Nah, next Monday is Easter Monday, so I will see you for the week after.
Okay.
Okay. Meantime, I'll look up some double equation questions and also I've given you a link to the AQA area of stuff, which has basically got all of what we were looking at, including past papers and the topics and everything for all your combined science of biology, chemistry, and physics. Okay, which then also has subject content, so bringing it out into the view I showed you earlier, which tells you what you need to know and what practicals you need to know for it. Okay,
Yeah, that makes sense. Thank you.
not a problem, right? Hear from you in a couple of weeks then.
Okay, see you.
Bye.